Hello students, today we are going to discuss about quantum physics. So the word quantum means in fixed amounts. We are going to see how quantum physics can be used to explain the nature of light. Light in this topic I mean all electromagnetic waves from radio waves to gamma ray. If you see some of the ancient theories about light, the first theory was put forward by Isaac Newton and this is called the corpuscular theory. What he told is light is made of particles called the corpuscles. As you can see, all the light from a candle to the sunlight, everything is made of particles. But his theory was discarded later because scientists observed the phenomena like interference, polarization, diffraction. In interference, you can see two waves can produce darkness. If it was particle, it will never happen. Like in polarization, we consider the components of vibrations of the wave. In diffraction, you can see the wave is spreading through the gaps. It won't happen if the light was made of particles. Corpuscular theory was discarded by the scientists because it could not explain these phenomena which you observed later. Now let's see what wave theory says about light. Wave theory says light is a wave, and wave means a continuous flow of energy. Now there are two important characteristics of a wave. One is the intensity, or what you call the brightness. For example, if this is a very dim red colored wave, how does a bright, very intense red colored wave look like? Wave theory says a bright red light look like this. What you can see is the amplitude has increased, but nothing happened to the frequency. Wave theory says intensity depends on the amplitude. As the intensity is more, the total energy reaching a point per second will also increase. The second characteristics of a wave is its frequency. Wave theory says if this is an orange colored wave, how does a blue colored wave look like? As you know, blue has more frequency than orange. So wave theory says a blue colored wave should look like this. It should have higher frequency, means there should be more number of waves reaching per second. According to wave theory, frequency just means the number of waves reaching a point in a given time. So it was considered as the correct theory to explain the nature of electromagnetic waves until the late 19th century. But towards the end of 19th century, they discovered something called photoelectric effect or photoelectric emission. Let's see what's the meaning of this. Photo means light. So what happens is if you consider a metal plate, there are metal atoms. Each atom has nucleus and there are electrons. So the electrons are pulled by the nucleus. So if you give electrons enough energy to overcome this attraction, the electrons can go out. So that's what's happening during photoelectric effect. You apply light and using the energy from the light, electrons are going away from the nucleus or they go out of the atom. This is called photoelectric emission. So if you apply an electromagnetic radiation on a metal plate, you can see the electrons are going out. Nowadays, we can observe this phenomenon very common, for example, solar panel. So this is a definition of photoelectric emission. Electromagnetic radiation falls on a metal plate and the electrons are emitted. If it has a sufficient frequency, I will come to that point later. So now we are going to see why wave theory failed to explain this photoelectric effect. Let's consider this example. The values I am giving are not realistic values. Consider a very bright red light which has 1000 joule energy per second. You can see the waves are really big because the intensity is very high. Consider a very dim blue light which has very small energy, like 50 joule energy is coming per second. So you can see very dim, very small waves. So wave theory says 1000 joule wave has more energy, and that's obvious. But when you apply the bright red light which has very big energy like 1000 joule to a metal plate, nothing happened. Even if you apply it for a long time, not even a single electron got emitted. At the same time, when you applied the very dim blue light, it's very dim, it has just 50 joule energy per second, very small waves. But still, a lot of electrons got emitted when you applied the dim blue light, but nothing happened when you applied the very bright, highly energetic red light. This proved wave theory to be completely wrong. Since the wave theory failed to explain these observations, we needed a new theory to explain photoelectric effect. That's what you call the particle theory or the quantum theory. Let's see what quantum theory says about light. Quantum theory says light is not a continuous flow, like wave theory said. Quantum theory says light is made of separate, discrete packets of energy. We call them photons. For example, if wave theory says this is a 100 joule wave, particle theory says it's not a single package. This 100 joule is made of separate packets of energy. The second point of particle theory is what decides the energy of a photon. It says the energy of the photon directly proportional to the frequency of light. Or when you want to change this proportion to an equation, I'm adding the constant, that is the Planck's constant. So energy of the photon depends on its frequency. Means if you consider the visible light photons from violet to red, violet has the highest frequency. So violet photons will be the most energetic photons in visible light. Then indigo, blue, green, yellow. The least energetic photon in visible light is red light, because red has the minimum frequency, so their photons will be really small energy. The same equation I can even write in terms of wavelength from the equation V equal to F lambda, or F is equal to V by lambda. I'm writing C by lambda because the speed here is a constant speed, which is speed of light, 3 into 10 to the power 8. The radiations with bigger wavelength, like a red color, will have the lowest energy for their photons. And the third point of this theory is one electron take only one photon. Means electrons cannot collect photons, because already you studied the atoms contains energy levels. In a solid, there are only two energy levels, valence and conduction. Valence means the last shell in the atom. Conduction means you are out of the atom. Conduction means the electron has gone out of the atom. If an electron is here, when it receives a photon, it can jump out. It is not allowed to stay in between. There is no possible energy for an electron in between. If the electron takes the photon, it should help it to go out. Otherwise, the electron will not take the photon. So using these concepts of particle theory, we are going to explain what we observed before. There are electrons surrounding the nucleus in an atom, and this particular example, I am considering the electron needs 8 joule to go out. Remember, 8 joule is not a very realistic value. This is just for you to understand. Now let's see what we observed before. I am applying a very bright red light. It has 1000 joule per second. Means the electron could get 1000 joule in every second. But still, not even a single electron is going out. So let's see the reason now using the particle theory. Particle theory says this 1000 joule is not a single package. 1000 joule contains photons. It contains a lot of red photons. Red photons are really small energy. So I'm taking just for an example 1 joule energy. Let's say each red photon has 1 joule energy. So how many such photons will be there in this beam per second? Totally we need 1000 joule per second, so there will be 1000 such photons arriving the metal plate per second. But the first photon coming has just 1 joule and the electron needs 8 joule. Will the electron take that energy from the photon? No, because taking 1 joule, it can't go anywhere. Every photon in the red color is just 1 joule energy. So the electron will not take even a single photon, even there are 1 million or 1 billion photons. But at the same time, let's consider the dim blue light. Blue photons will be more energetic than red photons because blue has more frequency than red. And the photon energy depends only on the frequency. So let's consider blue photons really big because they have more energy. I'm taking 10 joule energy for each blue photon. How many such photons will make the beam? There should be 5 such photons per second. Now let's see what happens to the electron. So first photon is coming 10 joule. Will the electron take? Yes, it needs just 8 joule. So what happens is one electron will absorb 1 photon and go out. So if there are 5 photons, exactly 5 electrons will get emitted. So even if the radiation is very dim, still you will see many electrons going out because each photon is enough to release the electron. Total energy is not important. Individual particles should have enough energy. That's how the particle theory correctly explains what you observe during photoelectric effect. Now let's see what happens to the remaining 2 joules. I told the electron just needs 8 joule, but you have all 10 joule photons. So what happens to the remaining 2 joule? This was first explained by Albert Einstein and he got Nobel Prize for that. He explained the 10 joule photon energy is used for 2 purposes. 8 joule to remove and the remaining 2 joule to give kinetic energy. So the remaining 2 joule is stored as kinetic energy of the electron. This was first explained by Albert Einstein and it's called Einstein's photoelectric equation. He explained the photon energy is used to remove the electron. We call a special name, the 8 joule in the example. You call a special name that's called the work function of the metal. It's a constant for each metal. And the remaining is given as the kinetic energy. So this is how the photon energy is used. Mathematically, you can write the photon energy HF is equal to work function has a symbol, it's a Greek letter phi, plus the remaining amount is kinetic energy. 10 joule, 8 joule to remove, plus 2 joule to move. That's a kinetic energy. The work function is the energy needed to release an electron from a metal surface. For it to be a constant, we define the work function only on the surface of every metal. These are the work function of some of the commonly used metals. But you can see the unit is supposed to be joules, but I'm using an alternative unit called electronVolt. I'll be talking about this in the coming slide. You are planning to make a solar panel. Which metal among these would you choose for the solar panel? The answer is cesium, because you want every light to release electrons from the metal plate. If you choose platinum, sometimes even gamma ray will not be able to remove electrons from the metal. I have a metal plate. Onto the plate, I am going to apply different electromagnetic radiations. Starting from radio, micro, infra, all the electromagnetic radiation I am separately applying on the metal plate. And I am going to find the corresponding kinetic energy of the electrons emitted from the metal plate. As you know, every radiation may not emit electrons because their photons need to be stronger or having higher energy. Now you can see in the electromagnetic radiations, radio wave has the lowest frequency. So their photons are really low energy photons. And gamma ray has the most powerful photon among the electromagnetic radiations. So let's say on this metal plate I'm applying separately each radiation, radio, micro, every radiation frequency I'm going to mark on the x-axis. In this example, let's say radio and micro. Their photons do not have enough energy to release an electron from the metal surface. So you don't see any emission happening when you apply radio wave or microwave. Their photons are really small. Let's say at infrared, it just starts. Like in the previous example, I told 8 joule you need to remove the electron. What if the photon has exactly 8 joule? It will be able to remove, but it cannot provide any kinetic energy. That particular frequency of light, it can remove the electron, but it cannot provide any kinetic energy. That's a starting point of photoelectric effect. That's called the threshold frequency. Threshold frequency is the minimum frequency below which no emission will occur. So generally this is the equation, but if the light has just the threshold frequency, there is no kinetic energy. So if the radiation has exactly threshold frequency, it cannot provide any kinetic energy for the electron, it can just remove. So in this example, infrared has the threshold frequency. In that case, when you apply the visible light photons, what will happen? Then what if you apply visible light? It has a greater frequency than infrared. Then what happens is it will remove the electron as well as it will give some kinetic energy because it has more energy in their photons. What will happen when you apply ultraviolet? It can remove and give still more kinetic energy. So as you go on increase the frequency, the kinetic energy of the emitted electrons go on increasing. I'm going to draw a line connecting all these points. Now, how do we know it's a straight line? Why can't it be an increasing curve? For that, you need to know what exactly is the gradient of this graph. So I'm going to find out which quantity is the gradient of the graph. For that, I have to equate the original equation to y equal to mx plus c. As you can see, kinetic energy is on the y-axis, so I'm going to make Ke as a subject. And on the right hand side, you will get hf minus phi. The meaning is, if you plot a graph with kinetic energy on the y-axis and frequency on the x-axis, the gradient of such a graph will be h and the y-intercept will be not phi, minus phi, negative of work function. Means the gradient is Planck's constant. As you know, the Planck's constant is a universal constant. It won't change with the experiments or it won't change with the type of metals you use. That's the reason why you should have a constant gradient. If you want to find the work function of the metal, extrapolate the graph to touch the y-axis, and the point it touches will be minus phi. The answer for phi should be a positive answer because phi is a type of energy. Now I am going to repeat the experiment with another metal plate. This metal plate has a higher work function. What does that mean? It needs more energy to remove electrons from this metal surface. What will happen to the threshold frequency? Before, infrared could remove electrons, but now infrared will not be able to remove because the work function has increased. Sometimes even visible light may not be able to remove. So let's say now only ultraviolet and above can release. Now what will be the shape of the graph? Will it be same gradient or more gradient or less gradient? Whatever metal you use, whatever light you use, the graphs should be parallel to each other because all the graphs gradient is same. The gradient is the Planck's constant, which should be constant for any line. Practically, how do you measure this kinetic energy? Because you don't even see an electron. So how are you going to measure its kinetic energy? In the next part, we are going to see actually how the values on the y-axis is obtained. So to measure the kinetic energy, I am using this arrangement. There are two metal plates and I am considering a lot of electrons on one metal plate. I am considering a lot of electrons in this metal plate. I am calling it as the cathode. Let's say I want to find out how much kinetic energy ultraviolet light can give to these electrons. So I am applying ultraviolet light onto this metal plate. What you can see is the electrons are emitted. They will reach the other plate. So there is a motion. If you complete the circuit, electrons will be moving through the circuit. You can just ignore this cell. I have put a very low voltage, so it won't make any difference. If you connect an ammeter, there will be a current in the ammeter because the electrons are moving in the circuit. Even though it's nanoampere, since the number of electrons are very less, but still there is a current because the electrons are moving through the circuit. Now what I'm going to do is, I'm going to increase the voltage. So when I increase the voltage, what you can see, the current decreased because what you can see, the electrons are now moving slower. Does that mean they get less kinetic energy? No, because the photons are still the same. They give the same kinetic energy to the electrons as before. But why they are slowed down? Because when the electron is trying to go up with their kinetic energy, we have applied a potential here. What happens is this positive terminal will pull the electrons down. So the cell is doing a work on these electrons. They are pulling it down to oppose the kinetic energy. That's the reason they are slowing down. I want to stop the electrons completely. So again, I'm going to increase the voltage. I'm increasing the voltage. Let's say at 3 volt, the current just became 0. The UV light photons still provide energy to the electrons. They are removed from the metal plate. They have kinetic energy, but still they are not moving because now the work done by the cell has become equal to the kinetic energy. The cell is now pulling more. So we are going to use this idea. Kinetic energy directly we can't measure, but work done by the cell we can calculate. This particular voltage, when you just stopped these electrons from moving, that particular voltage we call the stopping voltage. So at the stopping voltage, we can get the kinetic energy because it's equal to the work done by the cell. We know voltage is defined as work done over charge, or work done is charge into voltage. We are going to use that equation to calculate the kinetic energy. The charge here is charge of electron because we are dealing only with electrons. And the voltage is the stopping voltage. And we directly get the kinetic energy of the electron in joules. But there is an alternative unit of energy which is very convenient for this topic. And that unit is electron volt. Basically, electron volt is a unit of energy. Let's see how much energy is 1 electron volt. Let's consider two metal plates, one charged positive and one charged negative, so that the potential difference between them is 1 volt. If you release an electron from the negative plate, it will accelerate towards the positive plate, means it will gain kinetic energy. Let's calculate the kinetic energy gained using the same equation we used before. Kinetic energy is equal to charge into voltage. I am keeping in 1 volt. So the kinetic energy of the electron in 1 volt is 1.6 into 10 to the power minus 19 joules. This much amount of energy, in short, we call 1 electron volt. So 1 electron volt is always equal to charge of electron that many joules. So it's a unit of energy. The convenience of this unit is directly you can change voltage to energy. For example, if you keep an electron in 1 volt, it gets an energy of 1 eV. What if you keep the electron in a voltage of 100 volt? Directly you can get as 100 eV. You don't need to do any calculation. Directly you can get the energy by looking at the voltage. Let's see how the concept of electron volt is going to help us here. What you saw is we stopped the electron for a voltage of 3 volt. Now the question is, then how much kinetic energy will it have if it is in electron volt? The answer what you got is in joules, but if you use electron volt as the unit, here you stopped the electrons for a voltage of 3 volt, means the kinetic energy the electron had should be 3 electron volt. That's why you could stop it for 3 volt. I want to find the kinetic energy given by infrared light, but you found 3 eV is for ultraviolet. Now I am replacing this light by infrared. Can you tell me what would happen to the voltage you need to stop the electrons? As you know, infrared has a lower frequency than ultraviolet. Means infrared photons are going to be less energetic, smaller photons compared to ultraviolet. So they could give only less energy to the electrons. Means you don't need that much voltage to stop them. So the stopping voltage will be less if you use infrared instead of ultraviolet. Now we are going to plot the same graph what we did before, but this time directly from the measurement. So the measurement what we did here is actually the stopping voltage, not the kinetic energy. We actually calculated the kinetic energy using the stopping voltage. So what if you plot directly the voltage on the y-axis instead of energy? Means instead of Q into V, I am just plotting voltage. So let's see what difference it will make for the gradient and y-intercept. The kinetic energy is actually charge into voltage. I am making charge into voltage as a subject, but I am plotting only voltage on the y-axis. So I have to bring electron charge onto the other side. So this I am bringing to both terms. I am bringing the electron charge. I am equating to y equal to mx plus c. Means if you plot a graph with stopping voltage on the y-axis and frequency on the x-axis, the gradient would be h over e. In the previous graph with kinetic energy here, the gradient was h, but now it's h over e, and the y-intercept should be minus phi over e. The shape of the graph will not have any difference because the gradient is still a constant. Now we are going to see some of the observations during photoelectric effect which proves wave theory to be wrong and particle theory to be correct. For example, when I applied a very dim red light onto a metal plate, no electrons got emitted. But when I applied a dim blue light, many electrons got emitted. How particle theory successfully explains this and how wave theory failed to explain this. So we will see that. So what you observed is, as you increase the frequency from red to blue, if you go, you are increasing the frequency, then the emission occurs. Nothing happened to the brightness, nothing happened to the intensity of light, but only the frequency has increased. So the observation is there should be a minimum frequency, above that only this is going to happen. Let's see how particle theory successfully explains that. Particle theory says it's all made of packets of energy, and we know they are photons, and the energy of photon depends only on the frequency, or it's inversely proportional to the wavelength. And the third rule, one electron can take only one photon. So each photon should have enough energy, means each photon should have enough frequency so that it can overcome the work function. Work function means the minimum energy needed to remove an electron from the metal surface. But wave theory, you know, it's failing to explain the photoelectric effect. Wave theory says wave is a continuous flow of energy. So it doesn't matter whether it's a red light or blue light. Even if it's very dim, the electron could wait for a long time so that they can collect energies continuously because it's a continuous flow of energy. But this is not happening. You don't see electron emitted after 1 hour, 2 hour like that. If it has to emit, it will emit at the same instant you apply the light. Otherwise, it would never emit electrons. We have seen if it's a dim red light, nothing happens. What if you apply a bright red light, very powerful red light? You can see still nothing happens because the photons doesn't change. Red photons are still the same. The only difference is there are more number of photons. So if you compare the wave theory and particle theory, wave theory says when you increase the brightness, each wave gets stronger. But particle theory says when you increase the intensity, brightness, nothing happens to individual photons. They don't grow bigger. Instead, the number of photons increases. So, if a dim light couldn't emit electrons, even the bright light of the same color will not be able to emit electrons because the photons are just the same. Now, what will happen if you apply a bright blue light? So, I'm changing to a bright blue light. What you see is a large number of electrons are emitted because a bright blue light will have more photons. So each photon will release an electron. So the number of electrons emitted will be more when you apply a bright light compared to a dim light. So this is what you just observed. More electrons emitted when you applied a brighter light. The particle theory, the 3 points are exactly same in any explanation. The last point. So a brighter light means more photons per second. So it will emit more electrons per second. But wave theory says entirely different thing. Already, as you can see, the number doesn't change. What happened is each wave now became bigger. So the wave theory says if you increase the intensity, the kinetic energy of the electron increase, not the number. Each electron will be emitted with a bigger energy because the waves are now bigger. But this is not true. What we observe is more number of electrons are released, not faster electrons. Now, instead of the blue light, I am again going to increase the frequency. I am going to apply violet light. What difference do you observe? So when I apply violet light, what you can see is the electrons are now emitted with a greater kinetic energy. So if you talk about frequency, wave theory says if this is a low frequency light, this is a high frequency light. What you can see is the change happens only in the number of waves. Each wave is not becoming energetic. Instead, now there are more waves per second. That's what you call frequency for the wave theory. But for particle theory, frequency has some different meaning. For example, if this is a low frequency photon, this is a high frequency photon. Individual photons become bigger. So the kinetic energy given to the electron also will increase when you increase the frequency. But wave theory says when you increase the frequency, the energy of each wave doesn't change. Only thing happening is more waves are coming now. So that will result in the emission of more electrons. So what we observed is the kinetic energy increases as the frequency increases because Einstein's equation says as the frequency increases, the kinetic energy should increase because the work function is a constant for a particular metal. But wave theory, which fails, explains when you increase the frequency, when you go from a blue light to a violet light, the difference is more number of waves. So more waves reaches, it will release more electrons but with the same kinetic energy which is not observed. Now we are going to see an experiment. This is the experiment they first conducted to observe the photoelectric effect. So to start the experiment, you have to rub the metal part with a rod so that the entire region is now negatively charged. The entire part, the metal parts throughout this, even the metal is completely negatively charged. So due to this negative charge as a repulsion, this gold foil, this is a thin gold foil, is deflected and it's staying at an angle from the base part. You can measure the angle, how much deviation happened. Now you are going to apply an ultraviolet light onto the metal plate. So what you can observe is the deflection has decreased. As soon as you apply the ultraviolet onto the metal plate, what happens is the electrons are emitted from the metal and the repulsion decreases. A calculation question in this topic. So what is given is the work function of the metal in electron volt and the wavelength of light in meters. You are asked to find the speed of the electrons. So the only equation that is connecting all these quantities is Einstein's photoelectric equation. But the problem here is frequency is not given. Instead, wavelength is given. Another problem is work function is not given in SI unit. It's given in electron volt. So first I am going to change the frequency to wavelength. Now second thing is changing the electron volt. That is very easy. Directly multiply by electron charge. So you get the energy now in joules. Because all the quantities should be in SI unit. You cannot use electron volt if you are finding some quantity which is in SI unit. So I'm going to substitute everything. I will get the kinetic energy, but the question is asking to find the speed. So I have to again use half mv square, but the mass of the electron will be given in the formula sheet and you will get the speed of the electron. That's the end of photoelectric effect part. Now, is photoelectric effect the only phenomenon which proves wave theory to be wrong and particle theory to be correct? No, there are many other phenomena like that. We are going to study one more phenomena which proves wave theory to be completely wrong and could be explained only using particle theory, that is the existence of energy levels in atoms. Not like a solid, a gas will contain large number of energy levels. They are represented by horizontal lines. Those lines are symbolic. They just represent the energy of an electron inside an atom. The lowest energy state is called ground state and the higher levels are called excited states. Generally the electrons will be staying in the ground state because they have the tendency to stay in the lowest energy levels. All the energy levels values are indicated by a negative. You know energy cannot be negative, but what does that negative in these energy values represent? The meaning of that negative is the energy needed. So always the minus shows how much energy the electron in that particular level should get to go out of the atom, that is to reach zero. So zero is the highest possible energy for an electron and the ground state is the lowest possible energy. Now the electrons can jump to excited states by absorbing energy. You can provide energy by different methods. One of the methods is applying light. So electrons will absorb energy from the photons in the light and they will jump to high energy levels. But the energy what they receive from the photon should be exactly equal to the energy difference between the levels. Otherwise, they will not absorb the photon. For example, if this particular electron wants to jump to 1 eV level, it should absorb a photon of exactly 9 electron volt energy. So 9 electron volt energy photon can make them jump to minus 1 eV. For example, if they receive a 6 eV photon, where should they go? 10 to 4 because the difference is exactly 6. So let's say now they receive a very big photon like an X-ray photon. They can even go out of the atom. This process of taking an electron out of an atom is called ionization. And the ionization energy of this particular atom is 10 eV. Electrons can even jump in 2 steps. By absorbing a 8 eV photon, they jump to 2 eV. Now again they can absorb a small energy photon and jump to a small energy difference. So small photons, small frequency photons will help them to jump between small gaps and big frequency photons will help them to jump between big gaps. These electrons are not stable in the higher energy levels. They always have the tendency to stay in the minimum energy. So these electrons will come back to the ground state by releasing energy. And this releasing energy will happen in the form of photons. For example, if it's coming from 1 eV to 10 eV, it should emit a photon of exactly 9 eV energy. So a big frequency photon will be emitted because the gap is very big. If it jumps from -4 to -10, the gap is not as big as before. So it will emit a small energy or small frequency photon which might be resulting in a green color light. As we have seen before, electrons can even jump in 2 steps. First it's jumping from -1 to -2. As you can see, the difference in energy is really small. That's why it's emitting a very small energy photon, which is a red light. And again it's jumping a bigger gap. That will emit a still bigger photon, more frequency, more photon energy, which might result in the emission of an orange colored light. Again, it's jumping through a bigger gap, means it will emit a bigger frequency photon, maybe a green light. This is what practically you observe when you make the electrons to excited states, and when they come back, you see different colors are emitted. Let's summarize all the points about energy levels. So when you ask to explain about energy levels, you have to talk about ground state, excited state, how they are able to move between the levels, and mainly the energy of photon absorbed or emitted should be exactly matching with the difference between energy levels. The energy levels are specific for a particular atom, means no two atoms will have same type of energy level, and that idea you can use to differentiate between atoms, to identify which atom is present in a particular situation. Let's do some multiple choice question now. When you get a question in energy levels, you have to be careful if the word is absorption or emission. Absorption means the electron should be going up. Emission means it should be coming down. So the question is absorption, means answer could be A or D. Now the shortest wavelength. Which will be the shortest wavelength? As you know, the gap corresponds to energy of the photon, and energy of the photon corresponds to the frequency, not wavelength. Wavelength is inverse. Means shortest wavelength means biggest frequency, means biggest gap. So A is the answer. Now the emission. Shortest wave means the biggest frequency, biggest gap emission. So the answer is C. Emission of light with shortest frequency. Frequency directly proportional to the gap size. Emission means it should be coming down, so B is the answer. Highest frequency emission should be C. Absorption of highest frequency. Absorption means should be going up. Highest frequency means the biggest gap, should be A. The last question, which will result in the absorption of highest wavelength. Highest wavelength means shortest frequency, and it's D. Now let's do a calculation in this topic. The energy levels are given. You are going to calculate which transition, jumping between which energy levels will result in the emission of a photon with this much wavelength. The equation we have is the gap should match with the energy of the photon. But the photon energy is not given. Instead, they have given the wavelength of photon. So I am changing the equation to Hc by lambda. I am going to calculate the value, and I got the answer, but it will be in joules because I am using meters. But the energy levels are given in electron volt, not in joules. So you have to convert joule to electron volt, and for that you have to divide by the charge of electron. You got the value now in electron volt. This should be the difference. The gap should be this much. Now you are going to decide which of this gap matches with the energy 10.2. You can do some trial and error method, and when you subtract, you can see the difference between these two energy levels should be equal to 10.2. It should be jumping down. You should mark downwards because the question says it's the emission. One of the important application of these energy levels is atomic spectra. The word spectrum means lines of different colors. So this is called a continuous spectrum. It has all the colors in the white light. Let's imagine there's a source of white light, like a star. That white light passes through the outer atmosphere of the star. So there will be many gases present in the outer atmosphere of the star, and when the white light passes through these gas, what you can see is some particular photons will be missing. Some colors will be missing in the spectrum, and we call it as an absorption spectrum because some colors are already absorbed. Why some colors are absorbed? Because the electrons in the atom, they need energy to jump. Only if the photon energy is exactly equal to the gap. So they don't take all the photons, only the photons which will help them to jump to another energy level. All the remaining colors you will obtain. So the absorption spectrum will give you an idea about which gas is present in the outer part of the star. Like this absorption spectrum always you can use to identify which gas is present. All the electrons in this particular gas is now in the excited state. And you know they are not stable there. So what happens is these electrons will again jump back and they will release exactly the same colors which were missing in the absorption spectrum. The same photons will be released back. This is called an emission spectrum. So when you combine an absorption and emission spectrum, you will see all the colors, which is called the continuous spectrum. So even emission spectrum you can use as a characteristic of a particular gas. So is light actually a particle or a wave? Because some phenomena you studied before, like diffraction, polarization, interference, you cannot explain using particle theory. And some phenomena you learned later, photoelectric effect, energy levels, you cannot explain using wave theory. Finally, we conclude light is not a particle or wave. Sometimes it's a particle and sometimes it's a wave. Everything in the universe will have a wave-particle duality. So you believe light as a wave, but now it's behaving as particles during photoelectric effect. Similarly, what you believe as a particle, like an electron, can turn into a wave. Exactly symmetrical to this, a particle can become a wave. Is it possible? Let's see. When you send a beam of electrons through a crystal will have uniform arrangement of atoms. And you kept a photographic plate so that you will know if an electron hits the screen. So when a beam of electron is passing through the crystal, what you expect is uniformly spaced dots because the gaps in a crystal are uniform. So this is what you expect, but this is not what you observe. What you observe is alternative dark and bright patterns. The same type of patterns what you have seen in interference. The electrons are not behaving as particles. If they were particles, you would observe this, but you are observing some properties of wave. Means when the electron passes through that gap, they undergo two phenomena of wave. One is a diffraction, the other one is interference. So the electron suddenly turns into a wave. When it reaches the gap, it suddenly changes into wave. It suddenly changes into energy. It undergoes diffraction, it undergoes interference. So it is possible to change an electron into a wave. And this is what we do in electron microscope. So let's see why electron does that. Why not human beings? We have already learned in the wave topic, there is a condition for diffraction, that is the wavelength and the gap should be matching. Now, does an electron have a wavelength? Do we have wavelengths? Yes. Louis de Broglie explained every object will have a wavelength. Even a particle can have a wavelength which can be calculated using this equation where h is the same Planck's constant you have seen just now and p is the momentum. Momentum means mass into velocity. So any particle which is moving will have a wavelength. So you can even calculate your wavelength. And let's see why we are not behaving as waves like electrons. So let's calculate our wavelength. This is a Planck's constant divided by momentum. I'm taking just an example, a 60 kg person walking with a speed of 1 meter per second. When you calculate his wavelength, you will get about 10 to the power minus 35 meter. Why you will never able to become a wave with this wavelength? What is the reason? Because this wavelength is too small for any real wave existing. The minimum wavelength you know is gamma ray, which can go like 10 to the power minus 15 meter. So if you want to show the wave property, there should be a wave corresponding to your wavelength. Like you should have a wavelength between radio waves and gamma ray. Then at any point of time, you will change to a wave. But for electrons, when you use the same equation to calculate, you could get about 10 to the power minus 10 or minus 11 meter. This is the wavelength of X-rays. Means electron can anytime turn into an X-ray. When an electron passes through the gap, most of the atom's gap size, the atomic spacing or even the diameter of the atom is also in the order of 10 to the power minus 10 meter. So electron has got a good gap of its own wavelength. Its wavelength also 10 to the power minus 10 meter and the gap through which it's trying to go also similar. Means diffraction occurs. We have seen everything in the universe exhibits wave and particle property For example, light is behaving as a wave during diffraction or constructive interference, destructive interference, polarization, but suddenly it's changing to a particle during photoelectric effect. At the same time, electron, which normally we think as a particle during ionization or inside electrical circuits, it is undergoing diffraction and interference when you pass it through a crystal.